Good day.
Can you hear me?
Yes.
Okay. Is it true
I don't know.
that you have a room with like Star Wars Legos?
No. I have a handful of pieces of Star Wars Lego, only two of which are put together because who told you this?
My brother.
I who told him?
Andrew Herb
Oh.
told my brother that.
I've got a Costco bag full of them. When we were moving, my wife didn't want them stuck out, so she dismantled them. So I think one she gave me for Christmas one year that's put together over that way. And I did another one night when the power went out. But I mean, all like in our basement, there's only one kind of wall that's right behind the computer. That's like the load bearing wall for upstairs. So they're sitting down that way. Not having a finished basement, I don't really have any place to put them. Also, Ben likes to destroy things, so I don't like him playing with it. They're to be looked at. I also now have kids, so I don't have the money to go spend 80, 90, 100. The one I want is $200. The Millennium Falcon that's about that big, but Brittany won't let me buy that stuff anymore, so I don't know. But I do have.
McKay, I can't even hear you anymore.
He went to go get his bag of sand.
It's been frozen for me. I don't know if he's been showing anything.
Who what?
Are you back?
That's my little Millennium Falcon.
I can't even see. It's just frozen on your it's the screen's frozen. It's like one eye's closed and the other one's open.
I don't know how to fix that, but that's one of the ones. There's a little Millennium Falcon that I have. Leave and come back. Oh, there we go. I don't know. Da, 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 da. I think I have all of the naming things fixed. If for a question, I just put a Roman numeral, like if I said 1C and I put the Roman numeral for 4, that's what it should be, because I didn't want to type out the whole thing. Um, Roman numerals and some of the tricky things like europium and gadolinium were the ones that were a little bit tricky. Oh, hopefully Amy's computer hasn't totally messed up. Oh, there she is.
I want to refresh my page.
Oh,
Can you show me again so I can see?
it's just a little Millennium Falcon. That's
Oh,
all.
that's sick.
Yeah, well, there's that one. There's one that's about, I don't know, 2 feet long. Well, plus there's a new one. Like there's one that's about 2 feet long that came out ages ago, and then there was one for the Han Solo movie, and then there's one that came out. Oh my gosh, probably 15 or 20 years ago now. That's like 3.5 feet across. At the time, it was the biggest Lego set ever, and it was like $600. And there's a guy who teaches at KV who used to teach in Sussex that has one, and I'm jealous. But I mean, he bought it when he didn't have kids either. So I played golf. All my money is tied up in my golf bag. But nobody wants to listen to that. Actually, now that I think about it, I recorded all of that. So To hell with it. What am I doing here? We're, we're back over here. That's everything. We've got. All right. So I can't remember um, if I put these. I did that one. Did I export those? What? Oh, my airliner said the battery was dead, but it shouldn't be. Um, so today we're going to look at um, ionic compounds in water. We're going to talk about a couple things. Um, I'm not a super huge fan of net ionic equations, but that's just a personal thing. Um, but we need to talk about solubility, which is down here. Um, and if we don't get through everything, we don't get through everything. So if we're doing a predicting the products, just because I've had a couple of questions, the first part, the first thing we have to be able to do is identify what type of reaction it is, and that's why I kind of went through, well, apparently all but that one. That one's, whoops, that one's single replacement. Everything else on this page is double replacement. So when we have a single or double replacement, it's usually an ionic compound. Um, and then we need to do charges. Well, that's -1. This one has to be +2. That's +1. There's two of them. That one has to be -2. And what we're basically doing is rewriting ionic compounds, but I need to write an ionic compound with those two, and I need to write an ionic compound with those two. That one's acetate. It's an odd way to write acetate, but a formation reaction is usually, like, a lot of this stuff is with ionic compounds because it's things that we can figure out, even if it's single replacement. Well, acids are +1, that's -2. This, if it makes an ionic compound, will be +2. So I pair up the +2 and the -2. Pair up charges. Single replacement, +1, -1. That's going to make a -1. Decomposition, whatever elements are there. That's a typo. Double replacement. Formation, I just did copper +2. But that would be +1, -1, +2, -1. So, like, there's very few of these that are um, molecular compounds. If you missed that one, so be it. You're usually, when you may do a formation reaction like this, it's going to be your simplest compound with the two elements. So that one would be ammonia. There, I think, is a little bit more. This is kind of the big thing. This is, if you can go through a lot of, in particular, that page, well, because you have to write formulas to start. What is magnesium bromide? What is these? And then identify, well, that's a compound, that's an element, a single replacement, an element and a compound, single replacement. A compound and a compound, because it's got two words, double replacement, one thing in an arrow, and things like that. That one also is looking for, there's combustion. That's the one that's potassium, stuff like that. And then there's another page there where it's predicting products is tough, but we need to go up here. So where most of this happens is in water. And this is kind of tricky to do. Sorry, Brittany's just sending me messages from upstairs. Uh, Ionic compounds, if you take salt or potassium nitrate or any ionic compound, if you throw it into water, fundamentally it's not all packed together. It falls apart into ions. So this is, oh, well, it's right here. If I take sodium chloride and dissolve it in water, really we get a whole bunch of sodium ions with a state aqueous being dissolved in water. We get a whole bunch of chloride ions dissolved in water. Potassium sulfate is actually two potassium ions dissolved in water and some sulfate ions dissolved in water. And that's what the AQ, it's not a state, it's more an indication because it's something that's dissolved. Um, but this is why liquids, water with stuff in it conducts electricity. This is where we would go and you can put the little thing in and get the light to turn on um, and do a conductivity test and all of that, which is a good thing that water with ions conducts electricity because, well, our body is run on electricity. It's run with electric currents from your brain that tell your hand to wave or to shake your fist because your chemistry teacher's a jerk or whatnot. And we are also whatever percent water, 60, 70, 80, I don't know. But we have all of that water isn't just pure H2O. There's all sorts of ions. There's actually salt in it. There's sodium, there's potassium, there's chloride, there's slews of different ions. And because we have the liquid and the basically salt solutions, we can do like our body functions the way it does. Most reactions happen in terms of ionic compounds. You can't take two salts and just grind them together. Nothing will happen because everything's all stuck in it. When you split them apart and they start moving freely because the ions are separated, they're more free to interact. That's because you have a beaker of sodium and chlorine, you have stuff. It doesn't sit still. Things aren't just sitting there. They're all moving all over the place. So this is where, like, if we have that equation, and I think it's balanced. So if we take magnesium chloride, throw that in a beaker of water, throw that in a beaker of water, we don't have magnesium chloride altogether. We don't have lead sulfate altogether. We have magnesium, 2 plus ions. We have 2 chloride ions. Whoops. We have some lead ions. We have some sulfate ions. And they're all in, I mean, you would have 2 little individual beakers before you pour them in. So you've got beakers of these things that are floating around. And there's however many of them. We'll talk about concentration in a couple of weeks. Um, they're just floating around. Eventually, they start to run into each other, and that's when the reaction happens. Well, really the important part is this part here, which we're going to talk about why this is solid. Eventually, lead starts running into these guys. And lead and chloride, if you have enough, it's an ionic compound, but it's held together so tightly that water can't pull it apart. And that's fundamentally what makes these things happen. We get lead chloride. Those two stick together so well that they start to aggregate and you get more leads and chlorides and they start running into each other. And then you get, like we've got a level, you get this little kind of ball of solid that sits in the bottom, and that's the solid in there. Technically, that magnesium ion just it's still floating around, does nothing. It's sitting around doing nothing. And then the sulfate is still technically still floating around. So that's what the reaction is. We write them as pairs because, well, we make a solution of this by taking some solid magnesium chloride and throwing it in water. So that's fundamentally what we have. We have lead sulfate, lead 2 sulfate. We take that and we have that in a different one. When we mix them together, this is going to form. So this is what we're left with. We don't end up with those two together. We say they are because, well, they balance out and they have to balance. But really, that's the important part. The solid, the precipitate is the fancy word for it. So normally we would talk about writing a complete ionic equation. And when you do concentrations and quantities and all of that, well, that one's the same as the one before. So I'm going to do this one here. Um, Personally, you're looking at concentrations and it just seems ridiculous to do these simplifications, but FeBr3 is iron 3 plus, 3 bromides, because if I get for every one of those I put in solution, I get 1 iron and 3 bromides. We get some potassium ions. We get some hydroxide ions. And those all float around in their individual things. Then we put them together in one big beaker. Well, this says potassium and bromide don't really do anything. So technically, we still get potassium. We still get bromide. I don't know why I wanted to do -1. And then this as a solid. Well, if it's a solid, it's not dissolved. And we say that's a solid. Now we can balance that by putting a 3 there. Technically, now we need a 3 here. To get 3 bromides, we need 3 potassiums. So it balances, but I can also just do that to balance it. Um, but this is fundamentally what's going on in your beaker. And what a lot of people like are what are called net ionic equations. So I'm going to, and they have a place. Oh, potassium and bromide don't change. Apparently I didn't go down far enough. That's bromide on that side. That's bromide on that side. Potassium, potassium. So when something fundamentally doesn't change, we call them spectator ions because they're like what you guys are now. You're spectators. You're not, and it's through no fault of any of your own, you're not interacting like you would in a classroom or anything. And I mean, some of you would still not interact with many people in the class, but they don't change. So what some people like to do is say, well, I can ignore this, I can ignore that. The actual fundamental reaction in here is iron 3 plus aqueous plus 3 hydroxide aqueous goes to as a solid. Now, it that's perfectly fine. Um, it's something that we have to talk about. You need to be aware of it. Um, I don't use them a whole lot, but we have to. You get the same information here, and if you know that everything is splitting and falling apart, you can tell the things that stay in solution. That's the important part. We need to eventually do one of these double replacement reactions and then look at the states. But that's what we are going to talk about, I think, on to your next page. Um, so this is the reaction that's happening. There isn't really any reaction with potassium and bromide. They just sit there. You can filter that off and then evaporate it, and you can get it out at the end. But these only really work for single or double replacement reactions. They don't work for formation or decomposition. They show the things that, this is where they're useful. They show the things that change. So we have to balance, and some people will, I personally like to balance it before I eliminate everything, but you can say, well, balance it after. And we can do all sorts of different things. Well, whoops. H plus aqueous. Well, I'm going to need 2 of those because I would personally balance this first. Because we're balancing it first. Why is this 2OH, or why can you leave that there? Hydroxide goes to barium chloride, solid. And now this one's sneaky. That's a liquid. Is there anything, like, I can't split that up formally. That's water. It goes together and it doesn't fall back apart. That, for that particular reaction, is the net ionic equation. Because, well, HOH isn't on this side. BaCl2 is not on that side. I can't actually cancel something out. I can do aluminum. Well, that's a solid metal. Iron 2 sulfate. Let's balance this first. I need a 3 here, a 2 there, and a 2 there. So we'll put 2 of those, 3 of those, 3 of those. Oops. And you will run into some people who, if you're doing anything ionic and you're talking about ions and you forget the AQ, will mark things wrong. That's the way it is. Iron is a solid. That says it's aqueous, so we get 2 aluminum, 3 plus, and 3, whoops, 38 ions. So in this case, aluminum and aluminum 3 plus, well, those change. Iron 2 plus and iron, those change. Well, SO4 2 minus and SO4 2 minus, goodbye. So the net equation, 2 aluminum solid plus 3 iron 2 plus. And this is an instance where the coefficients now they don't matter ish. Iron solid, well, that's aqueous, and 2 aluminum. So the net equation is aluminum solid reacts with iron 2 plus, producing solid iron and aluminum ions. This, where you have, when you do a net equation, technically any of these single replacement, and where did my cursor go? These ones are called redox for reduction and oxidation, or electrochemical reactions. Whoops, sorry. Because the charge of this is different from the charge of that. The charge of this is different from the charge of that. Now, unfortunately, in New Brunswick's curriculum, when they revamped the chemistry one, and there used to be a small unit on redox chemistry in grade 12. And now there's not. Um, Anytime you have charges changing, a double replacement reaction, well, that's H plus 1. Technically, that's still formally plus 1. That's minus 1. The charges aren't changing here. But in these single replacement reactions, like chlorine plus oh, we need two of those and two of those and two of those. So we get two. So if we do this reaction, well, sodium is the same on both sides, so that goes away. Chlorine gas plus iodide ions goes to chloride ions and iodine. No charge, minus one, no charge. It's the same sort of thing. You can have double replacement reactions where it is one of these ones, but it's just a lot less common. So the other thing we need to kind of worry about, which we'll talk about, I don't want to do that, is precipitates. How do I know looking at that that's a solid? How do I know that looking at that there's a solid there? There's been a couple equations that I've said, oh, well, this one's a solid. And it's because I have a bit of experience. It's because I have parts of this silly table memorized. So a precipitate, for the lack of a better, I don't know where the word comes from, uh, you mix two solutions together, you get a solid. That solid that's at the bottom is called a precipitate. And we predict whether or not they'll happen with, there's some rules of solubility, there's numeric charts that you'll see if you take chemistry 12, um, but there's just a whole bunch of different rules. So this is some of this information in chart form. Anything with an alkali metal or ammonium is going to be soluble. So this I snipped out of, if you have your periodic table at home, and this top right corner on the back, it says solubility of some common ionic compounds in water at room temperature-ish. It's technically that's 25 degrees, but that's, they're fairly straightforward. So this has hydrogen, sodium, ammonium, potassium. Anything that's got potassium, rubidium, and those ones are soluble. Anything with nitrate or chlorate, NO3, ClO3, this says perchlorates and acetates. Anything that has any part of that is considered to be soluble, with the exception of some of silver acetate, um, mercury 1 acetate. I mean, I've never seen cesium perchlorate or rubidium perchlorate, so it's really not that big of a deal. And then what we're looking for these as part of a compound. And it says very soluble and slightly soluble, and you'll talk about that more in chemistry 12. These are, anything that's this plus any one of those is not going to make precipitate. Anything down here, and PPT is I don't know which T it is, precipitates. That's the shorthand for is something going to be soluble. Fluoride with most things, but fluoride with lithium, magnesium, calcium, strontium, barium, iron 2, technically is mercury 1, and lead 2. Fluoride with any of those, chloride, bromide, and iodide with any of those are not soluble. Carbonates, well, the small plus 1 ions are soluble. Everything else, apparently lithium carbonate is soluble. Carbonate, phosphate, sulfite, uh, that's, I think that's supposed to be IO3 minus 1. This one down on the bottom is oxalate, which is why rhubarb leaves are toxic because of oxalic acid. Sulfide and hydroxide, I think somewhere down here. That's the old table that we used to have. And nitrate, acetate, carbonate, phosphate, sulfite, sulfate, hydroxide. I guess technically it's got all the same stuff. Whoa, that is not what I wanted to do at all. Um, and we'll probably stop here in a second, give you a break. But what we need to be able to look at is something soluble? So in lithium bromide, well, lithium's not there. Lithium's not there. Oh, there's bromide. So we have to look. We've got most. Well, that doesn't help us. Is lithium part of those things down on the bottom? Lithium is not copper, silver, all of that. So this is a yes. It's soluble if it's not one of those. Barium nitrate. Well, I don't see barium up here, but I do see nitrate. Most are soluble. Is barium nitrate one of those exceptions? No. So that's soluble. I've never, ever once come across. I, I'm sure there are nitrates that are not soluble or are slightly soluble or form precipitates. I've never honestly seen or heard any of them, but I'm sure it's a possibility. Calcium's not up there, but now sulfate. So, uh, oh, sulfate. Sorry. Most are soluble except for, oh wait, calcium and sulfate, it says is not soluble, so we would say no. Chloride is here with lead 2 plus is there, so that's a no. Calcium carbonate, potassium carbonate, and cadmium chlorate. I'm going to stop here because it's 2:30. Um, go through that chart and try to predict whether or not those are soluble or not. There is, and then tomorrow we'll look at kind of a summary, the process, can we change things, use coefficients, and I'll do some of those. And that's the end of chapter 11, so I'll probably have to find some stuff for an assignment there. Um, is any questions? Oh, we lost somebody who was here earlier. It's funny, there's like the, well, 5 or of you who are always here. Kathleen normally is, but she told me why she's not here and won't be for a little bit. But I'm still getting 15 assignments, so I was like, well, either a whole bunch of you are cheating or people are watching my videos or other videos and whatever works. I'm not going to say anything in particular, but I'm assuming people aren't cheating, but
Mr. McKay,
yes.
the last 2 pages that we were supposed to do last or yesterday or whatever, are the answers to those on
the completed or something like that? Like, what are the answers to those every
Uh,
time you do that?
if they're not there now, oops, sorry, I didn't mean to do that. They will be shortly. I'm in chemistry. Come on, 5 arrow. Well, apparently yesterday at 10:51 is when I finished them. So, um, wow, the page down thing doesn't really work. If they're not there, they will be shortly. Oh, no, yeah. So that it's that part and those ones are there now. And I'll add what we did today. Not that there's a whole lot. But did what I said at the beginning help a little bit?
Maybe. I don't know. I'm still lost. It's
Uh,
fine.
well, and these are tricky, but it's really about for single and double replacement. Those are the ones that are the most common. Is 99% of the time they're ionic compounds. So if it's an ionic compound, what charge is it? If it's a single replacement, what charge would it be when it's in a compound? And once you have the charges, you're just like the goal is to pair them up is the most straightforward I can kind of go with it in this case, if that helps. But try it. If you have more questions, let me know and we'll try to find some way to get that figured out.
Okay.
Okay. Have a good afternoon.
You.
You're welcome.